In this lesson, we'll be discussing some theorems about variability. So the first theorem we're going to look at is called Chevys theorem. All these theorems are going to be dealing with different types of data, obviously, since we're talking about statistics. So given any n measurement, so it doesn't matter how many pieces of data you have, at least 1 minus 1 over k squared of the measurements must lie within k standard deviations of the mean, for k being greater than 1. So it's just a theorem about where your different data points have to lie within standard deviations. So in other words, we could say at most 1 over k squared of the data can lie outside. So our data, our interval would be the mean minus k times the standard deviation. That would be our lower end, and then our upper end would be the mean plus our constant times the standard deviation. So there's a range there that a lot of the stuff has to lie between, or we could think of it at most 1 over k squared could lie outside of that. So let's go ahead and test this theorem or use this theorem. What proportion of the data must always lie within 3 standard deviations of the mean? Well, to apply Chevys theorem with k equals 3, we have 1 minus 1 over k squared. Minus 1 minus 1 over k squared, we're just going to have 1 minus 1 over 3 squared, because that's the k that we're speaking of. And then that's 1 minus 1/9, which is 8/9 of our data within those standard deviations. So let's go ahead and take a bunch of data and check this out. So we're still going to stick with the k equals 3. So we know 8/9 has to lie within those standard deviations. So we have all these pieces of data here. I believe there's 16 of them. Sorry, there's 18 of them. So what we want to do, we do have to do some of our grunt work up front. We need to find the mean, and then we need to find the standard deviation. So that does take some work up front. So we would add all these together, divide by 18 to find the mean, and then work through the process of finding the standard deviation. So I'm not going to do that here. I'm assuming you know how to do that. So our mean is 9, and the standard deviation ends up being 2.59. Now we want to find out if it lies within how much lies within 3 standard deviations. So we take our interval that the things can lie between. So we're going to have our x bar, or our mean, minus 3 standard deviations. So 3 times 2.59, and then we're going to take find the high end, the upper part of the interval, by taking 9 plus 3 times 2.59. So there it is plugged in. We can evaluate that. We get 1.23 and 16.77. Well, we want 8/9 of our information, or our data, to lie in between those data points. And we notice that the only one that lies outside is this 1 here. So that's 1 out of our 18 pieces of data fall outside the region, and we could have had 2 values. So just one value lies outside, so that's 1/18, which is definitely less than 1/9. We could have had here that says 1/9 times the 18, because 1/9 could lie outside. We know that from the previous example. So 1/9 times 18, we could have had 2 to be allowed outside. Next, we're going to talk about an idea of mound-shaped data. Mound-shaped data, as seen below here, is a set of data in which the graph of frequencies, so this is how much each number that we might have here appears is roughly symmetrical, and the mode is in the middle. So there's mound-shaped data, which is really important for statistics. Our next theorem, so our first one was Chebyshev's rule. Our next one is the empirical rule, and this has to do with mound-shaped data. So given a set of data that is mound-shaped, approximately 68% of the data will fall within one standard deviation of the mean. 95% of the data will lie within 2 standard deviations, and 99.7%, so almost all of it, will lie within 3 standard deviations of the mean. So that's the empirical rule, and we're going to test that out a little bit. So use the data shown, check that it's roughly mound-shaped, and show that the empirical rule implies. So what we would want to do is we want to get our data. We would want to find how much of each value we have. So looking through here, we might want to put it in order. So it looks like our lowest is a 4, and our lowest is a 3. We just have one of those. We have a 4. And so we would want to organize that. Let's go ahead and find x bar and the standard deviation. Same thing as we would do in the past, add them all together, divide by the number of data values. So our mean is 7.6 and with a standard deviation of 2. We'll go ahead and make a frequency table to check if this is actually mound-shaped. So here it is. We have 1 3, 1 4, 1 5, 2 6s, 3 7s, 5 8s, 4 9s, 2 10s, and an 11. Let's go ahead and graph that. And it is somewhat mound-shaped. It looks like it's a little bit to the side, but we only have one of each of these, so it is somewhat mound-shaped. And now we can go ahead and check to see if the empirical rule holds. So we're going to find one deviation. So remember, we want to see if 68% lie within one deviation, standard deviation, which means on either side of the mean, below the mean and above the mean. So within one deviation, standard deviation, we have our mean minus our standard deviation, which was 2. So again, here's our mean and our standard deviation. So we have 7.6 minus 2 and 7.6 plus 2. Gives us this interval here. There are 14, so we could look over here. So we want, really, all these are whole numbers. So we want numbers between 6 and 9. So we have 2 6s, plus 3 is 5, plus 5 is 10, plus 4 is 14. And that's 70% of our data. So if we take 14 out of the number of, so we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 pieces of data. So we could do 14 out of 20, which is 70%. So it fits, it works. We were saying at least 68 should be in there. 2 standard deviations. Well, we're going to take our mean and add and subtract 2 standard deviations from that. So 2 times s would be 4. So 7.6 minus 4 is 3.6, and our mean 7.6 plus 4 is 11.6. And we want to check how many are between. So this is 4 and 11, which if you count those up, you will have 19. And really what we could do here is, instead of counting all those, we realize only one lies outside, so that's 95%, which is what we wanted. And then the last one, within 3 standard deviations, so we want to do 7.6 minus 3 times 2, which was our standard deviation, which gives us 1.6, and 7.6 plus 3 times 2 So 7.6 plus 6 is 13.6, and by the empirical rule, 99.7 should lie in that range, and all of them lie in that range, so 100% lie in that range, so that works. So that's the empirical rule, which is important for mound-shaped data. And then the last thing, which we'll actually get into a little bit more, the central limit theorem. If you repeatedly choose random samples, each of size n, where n has to be greater than or equal to 30, so you have a population and you keep choosing just 30 random, maybe people or something, and compute the mean for each sample, so the mean of something, maybe age, we don't know, maybe height. What will happen is the graph of the frequency distribution of the population of all sample means will be mound shaped. So if you keep finding a bunch of samples of 30 or more, find the means, and then make a distribution table or frequency distribution of those means, it will be mound shaped. And we'll look at that more as we'll look at a lot of the standardized tests have this mound shaped data and use that. And that is it. And that mound shaped data, we'll talk about the bell curve. Now that's really it.